Here in section 8.2, we're going to be learning techniques for solving systems of equations that are much better than the ones that we learned in 8.1. 8.1 was the graphing method, and you had to have graph paper and a ruler, and you had to draw really accurately and think about intercepts and slopes. These techniques that we're going to learn today don't require any of that. They're just pencil and paper, and most students get the hang of these ones very quickly and much prefer them over 8.1's graphing method. The first technique we're going to learn is something called the substitution method. And here are the steps for the substitution method. Step 1, pick either equation, and in that equation solve for either one of the variables. Now, when you get to pick, there are good choices and bad choices. You can make any of them work, but you'll probably have a better time if you make a wise choice. In this case, I think the best choice is to pick the top equation, because it's a little simpler, and solve for y, because that's a little easier to solve for. All I have to do is move the 2x to the other side, and I've solved for y. Then the second step is plug in for y in the other equation. So in the other equation, where we used to have y, we're going to put in the thing that y is equal to. Y is equal to negative 2x plus 10. So instead of writing y, I write negative 2x plus 10 instead. And that looks a little messy for a second until you realize, hey, there's only x in this equation now. We only have one variable. So if there's only one variable, do the thing you know how to do and solve for x in this equation. So negative 4 needs to get distributed in. We need to collect our like terms. The 7x and the 8x makes 15x. The 40, we're going to move that to the other side. So we've got 15x equals 45. And then divide by the 15, and we've got x equals 3. That's not the end of the problem, though. There are two variables in this system. We can't just solve for x. And another thing that I want to mention to you is always write your answer in point notation. That's going to be the expectation for these sorts of problems. Always write the answer in point notation. That'll help you avoid the mistake that I'm about to make here if I'm not careful and just stop with x. X equals 3 feels like the end of the problem, but it's not. We need to solve for y also. So take x equals 3, plug it back into one of these equations we've got up here. I like this one. It's not the only choice. I could have used any of them. And we get y equals negative 2x plus 10. So y comes out to be 4. So the answer here is 3, 4. Remember, we're talking about the intersection of two lines. And if two lines intersect, they're going to intersect at a point. So you needed to give the description of that point, its coordinates. Now, you'll also remember from section 8.1 that there are 3 types of answers that you can get when you try to draw two lines. You can get a point of intersection like we got here, but there are 2 other special cases. We need to learn what those special cases look like if you're solving things algebraically. So here are 2 very simple problems. I've already done the first step. I've already solved for x in the second equation and y in the other pair of equations. So for the first pair here, let's plug in for x in that top equation. So we're going to have 5 minus 8y plus 8y equals 3. And you'll see pretty quickly that this is not like the problem we did a second ago. Something different is happening. The 8y's are going to cancel here. Minus 8y plus 8y just totally cancels out. And just like we learned way back in the first chapter of Algebra 1, an equation like this that has no variables and is making a false statement, it says 5 equals 3, and 5 is not equal to 3, that means there's no solution. So algebraically, without drawing the picture, we can tell that this system of equations has no solution. And remember what that means for the picture. If you were to graph these two lines, these two lines are going to be parallel lines. They don't intersect anywhere. The other special situation to take a look at, I'm going to illustrate over here. And again, I've already got one of the equations solved for y, so I'll plug in for y in the other equation. 3x minus 3x plus 5 equals negative 5. Don't forget, you got to distribute that minus sign in there. If you don't do that, you might have the wrong result to this. The 3x's cancel, but there's a subtle difference here. Yeah, all the variables canceled, but the statement we have at the end is a true statement, not a false statement. This statement is saying negative 5 equals negative 5, and that's true. So this is not no solution. This is the other special situation. And remember the vocabulary. We don't say all real numbers because the answers here aren't numbers. The answers here are points. And we don't say all points because plenty of points are not on the duplicate line. The proper vocabulary is infinitely many solutions. But other than the change of vocabulary, the idea that you get a bunch of answers when you have this sort of result, that's the same as it was back from our first chapter in Algebra 1 a long time ago. There is a second technique. The substitution method we started with here is not the only way to solve with pencil and paper without graphing. There is a second technique that's a little faster and that you might like better, but it takes a little bit more thinking in the beginning, so it's a little more challenging. This other technique is called the elimination method. And the elimination method is based on one key idea that's been sort of lurking inside of algebra all this time and you haven't really known about it. The key idea is it is legal to take two equations and just add them together. I'm going to put quotes on legal because it's not like anything is actually illegal in math. It just doesn't work. So in this pair of equations I have here, I could theoretically just add the two equations together, straight up and down. So I would have 5x minus 3x is 2x, 8y and 4y makes 12y, 22 and 18 makes 40. But that doesn't really accomplish anything useful. The tricky part of the elimination method is that you want to prepare the equations very carefully ahead of time so that when you add the two equations together, something useful happens. And I know that sounds kind of mysterious, but watch what happens in the first couple of steps of this problem and see if you can imagine trying to do that yourself. What I'm going to do here is I'm going to take the top equation and I'm going to multiply it through by 3. Everything in the equation times 3. So I'm multiplying on the left and on the right by 3. So that'll be 15x plus 12y equals 66. And in the second equation, I'll go through and I'll multiply everything by 5. So that'll give me negative 15x plus 40y equals 90. Now, that just made all the numbers bigger, which might seem like a bad idea, but if you imagine adding these two equations together, can you see what the advantage is? What will happen here is the x's will cancel each other out. 15x minus 15x, add them up, you get nothing. 12y and 40y will have 52y. 66 and 90 will have 156. But notice we're almost done already. We've already figured out what y is. Well, aside from dividing, we have to take the 52 and divide by it. But that's not very hard to do. This is a lot faster than the substitution method. It gets us to an answer a lot quicker. But remember, this is not really the end of the problem. You also have to find x. There are some choices you could make. One thing you could do, and this isn't particularly sophisticated, but it works just fine, is you could take y equals 3, and you could plug it back into one of the equations we started with and solve for x. Or, alternatively, if you're starting to like this technique, you could start the problem again, redo it, and set it up so that the y's cancel instead of the x's cancel. Because I was very careful when I picked the 3 and the 5 that I used a second ago, because I knew that would make the x's cancel. I could, alternatively, instead of using 3 and 5, I could have done the problem like this. I could have taken the top equation and multiplied everything by -2, which would have made -10x and -8y and -44, and just left the bottom equation alone. I guess technically, if I want to say everything's multiplication, I could say multiply by 1, but really just leave the second equation alone. And this time, when I add them up, it's not the x's that cancel. This time, the y's cancel. -8y, +8y cancels out. And I get -13x equals -26. Divide by the -13, and we've got x. So eliminate one time in one way to get y, eliminate a second time in a different way to get x, and you've got x and y. Either technique that we've learned today will work on any problem. You can use substitution on any problem. You can use elimination on any problem. But there are plenty of situations where one technique will be better than the other technique. So the trick is to look at a problem and know which technique you want to use on that one. And you won't really know which technique will work better unless you've practiced both of them and you're pretty good at each one of them. Otherwise, you're only picking the technique that you've practiced, and you aren't necessarily picking the better technique. So my suggestion is, as you work your homework here in section 8.2, try to use both techniques as much as you can. Don't give up on one technique if it's difficult at first. Put in the time until you're at least pretty good with both of them.